Okay, and now we'll do some slightly more complicated ones. This is circuit analysis level 3. First one here. How much power is provided by the voltage source? Well, we'll need to know the current through the voltage source and the value of the voltage source itself to work that out. First of all, let's try and get the current. Well, we know that there's a total of 37 nanoamps flowing down here, and there's no current flowing through the voltmeter because, being an ideal voltmeter, it has an infinite resistance. So all of that 37 nanoamps here must be coming through either this or this. And we've got 11 nanoamps flowing that way, so the total current flowing into this node here must be 11 plus 37, or 48 nanoamps. So we know we've got 48 nanoamps flowing across this resistor. And if we've got 48 nanoamps flowing across the resistor, and the resistance is 82K, then the voltage across this resistance must be 3.936 millivolts. Right, and it's going this way, so this point here must be 3.936 millivolts above that point there. That makes the total voltage at this point here in the circuit 3.936 millivolts plus 19.1 millivolts, which would be about 23 millivolts. So we've got about 23 millivolts here. We also need to know how much current is flowing through this voltage source. And we know we've got 11 nanoamps going this way, and we also know we've got 48 nanoamps going this way. So there must be, if 11 nanoamps is flowing in, 48 nanoamps is flowing this way, there must be 37 nanoamps going up through here. So the current through that voltage source is known. It's 37 nanoamps. Oops. And the voltage across that voltage source is known. It's this one down here in the Y box. And the product of those two is the power. Great. Next. Okay, here we want to know how much power is dissipated in the current source. And again, we'll need to know the value of the current source and also the voltage across the current source. Well, it's a perfect ammeter, so there is no voltage drop across it because it has no resistance. So we know the voltage difference between ground and this point in the circuit up here is just 20 millivolts. So the voltage across this current source must be 20 millivolts. We know that. Now then, the current through the current source here. We know that this point up here is at 20 millivolts, so this point up here must be at 22.1 millivolts. So the current through this resistor here must be 22.1 millivolts divided by 91K. And that's the current flowing down through here. The current flowing up through here and along here is 563 nanoamps, and that must be the current flowing down through here plus the current flowing down through this current source. So we know that the current through the current source will be 563 nanoamps minus the current flowing down through here, which is X. So we now know the voltage across the current source, and we know the current through the current source, so just multiplying the two together, which would be 20 millivolts is the voltage, and what we worked out here in Y is the current. That will tell us the power being dissipated in the current source. Great. Next. I'll do this one as well to show you that there are two alternative ways of solving this type of problem. The way that we've been doing up until now, and also using the method of superposition, which can be a little bit more straightforward, although it is usually rather more long-winded as well. The way we've been doing this type of problem in the past is to say, right, what is the current flowing through that resistor? And here we can see that there's 420 nanoamps flowing up through here, and 110 nanoamps flowing this way, right to left, because there's minus 110 nanoamps flowing left to right. So the total current flowing into this node at the top here would be 530 nanoamps. And all of that current must flow out through the resistor because no current can flow through an ideal voltmeter. So we've got 530 nanoamps flowing through a 2K7 resistor, which means that the voltage across the 2K7 resistor would be 1.431 millivolts. We also know that from here to here is 671 microvolts, and we know that this is at a potential of 1.431 millivolts above here, so the potential there must be 671 microvolts minus 1.431 millivolts. That's the potential at that point there. So the voltage of this voltage source here must be minus Y, or in this case 760 microvolts. 760 microvolts. Fine. What's the other way of doing it? Well, use the principle of superposition. And that means that we can treat each of these sources individually. We can do that provided they are independent sources. They don't depend on each other, which here is true. In that case, we can first of all simplify this circuit by only considering this source first. All other current sources we replace by open circuit, and all other voltage sources we replace by a short circuit. That would mean that the circuit would become something that looks like this. Right, now with that circuit it's quite easy to work out what the voltmeter should read, because we have a current of 420 nanoamps flowing through this resistor here. So that would be a contribution to V, I'll call it V1, that's the reading of the voltmeter in this circuit, would just be 420 nanoamps times 2K7. Next source, let's just consider this source. It's a 110 nanoamp current source going this way. Again, we'll replace this with an open circuit and this with a short circuit, and that would end up with a circuit which effectively looked like this. Once again, we can work out what the contribution to V would be here, what the voltmeter would read in this circuit, and that would just be 110 nano times 2K7. And finally, we'll just consider this voltage source and forget the two current sources. And in that case, the circuit would become equal to this. Now, there's no current flowing through an ideal voltmeter, so there's no potential drop across this resistor because there's no current flowing through it. So the voltmeter would just read minus the voltage of this voltage source. Minus because the voltmeter is wired up with the arrow pointing up, and this voltage source is wired up with its positive terminal to the bottom. So in this case, we'd say that the reading on the voltmeter is just minus the unknown voltage. Now we can apply the principle of superposition and say that with all of these three sources combined, the total reading on the voltmeter will be the sum of these three components. And we know the total reading on the voltmeter. We can see it. It's 671 microvolts. And that must be equal to V1 plus V2 plus V3. Which means that since V1 is 420 nano times 2K7, and V2 is 110 nano times 2K7, and V3 is minus our unknown voltage source. Our unknown voltage source must be equal to 420 nano plus 110 nano times 2K7. I've just combined these two terms together. minus 671 microvolts. Taking this term over onto this side of the equation and this term here over onto this side so that it becomes positive. And that's an expression for our unknown voltage worked out by superposition. We could try it, just type it in here. 420 nano plus 110 nano times 2K7 minus 671 microvolts, and that gives us 760 microvolts, which is the same answer we got before, although it took rather longer. It's just an alternative way. Okay, that's it. Level 4 circuits are rather more interesting and more fun. I'll leave them up to you.